So question 7. A sequence of figures is made from squares of unit length. The first three figures in the sequence are shown below. So figure 1, see we're looking at 3 squares there. Figure 2, we're looking at how many? 5 squares there. And figure 3, we're looking at 7 squares there. So you notice the amount of squares going up by 2. So if we were to draw figure 4, of course you'll draw back figure 3. So figure 4. So figure 4 will look, let me just change this to. So figure 4 will be this. So you add, so you add in, so the amount of squares increasing by 2, right? So that would be 1, well, and then 1 more there. 1 more there. So figure 4 should resemble that. Alright? 7 squares. So we just add two of the squares, 2 of the boxes to figure 3 to get figure 4. So figure 4 should have 9 boxes. So now we are at 7b. Study the pattern of numbers in each row of the table below. Each row relates to one of the figures in the sequence of figures on page 22. That's the page above. Some rows have not been included in the table. So figure 1, there were 3 squares, perimeter 8. Figure 2, 5 squares, perimeter 12. Figure 3, 7 squares, perimeter 16, and so on. So notice we are asked to find the missing. So let's see if we can pick up a pattern here. So notice the pattern I'm seeing here between the number of squares and the perimeter of the shape. So to move from a number of squares to a perimeter, we double the number of squares and add 2, you get the perimeter. Look at double 3, you get 6, add 2, you get 8. Double 5, you get 10, add 2, you get 12. Double 7, we get 14, add 2, we get 16. So I imagine doubles for this one. Double 43, we get 86, add 2, we get 88. So I imagine this would be 88. And which shape would this be now? Which figure would this be? So this pattern. So notice, yes, let's see how the number of squares relate to the number of figure. If you compare the figure to the number of squares, notice you'll double and add 1. So to move from the amount of figure to the number of squares, you double the figure, add 1, you get 3. Double 2, add 1, you get 5. Double 3, add 1, you get 7. Double 4, add 1, you get 9. Double 9, you get 18. Add 2, you get 20. Alright, so to move from figure to number of squares, so you double the number of figure and add 1 to get the number of squares. And to move from number of squares to a perimeter, you double the number of squares, add 2, you get the perimeter. That's the pattern here. So n, to get a number of squares with double n, so you multiply n by 2. To double something means to multiply it by 2, right? And we add 1. And to move from number of squares to perimeter of the shape, with double 2n plus 1. And add 2. And just noticing, yes, and add 2. Alright. Another way to look at it, to move from figure straight to perimeter, you multiply the figure by 4 and add 4. I guess that would work also. So you multiply 4 by 1, you get 4, add 4, you get 8. Multiply 4 by 2, add 4 by 2, you get 8, add 4, you get 12. 4 by 3, 12, add 4, you get 16, and so on. 4 by 4, 16, add 4, you get 20. Or I could say 4n. I guess this would be 4n plus 4. Alright. And if you expand it, you realize, if you expand the brackets, you realize you'll end up with 4n plus 4. Alright? So that should be it. So 43. So would have doubled the figure and add 1. So this would have to be 22, right? So double 22. No, 21, sorry. Double 21, we get 42. Add 1, we get 43. So that should be our table. Notice we can change this. If we expand this bracket, we get 2 times 2n, that's 4n, plus 2, plus 2, so that's 4n plus 4. Let me also rewrite this as 4n plus 4. That would be way neater than what we originally had there. Determine the relationship between the number of squares and the perimeter P of a figure. Determine the relationship between the number of squares, which is S, and the perimeter of P of a figure. And the perimeter P of a figure. So the number of squares S is equal to 4n plus 4. Oh no, they want the relationship between squares and perimeter. So in other words, to move from squares to perimeter, just rewrite this. So the perimeter is equal to 2 times the number of squares plus 2. So notice perimeter. So the perimeter equal 2 times the number of squares. So for example, 8 is 2 times 3 plus 2, 12, 2 times 5 plus 2, 16, 2 times 7 plus 2, 20, 2 times 9 plus 2, 88, 2 times 43 plus 2, and so on. Alright, so the perimeter is equal to 2 times the number of squares plus 2. That would be the relationship. So question 8, the diagram on page 25 shows 6 points of the function y equal 3x plus 1 over x. The coordinates of these 6 points are given in the table below, and we have the table there with the x and y values. Complete the table by calculating and inserting the missing values of y. So the missing value of y is when x is 0.5. So y, to get this missing y value, so we have y is 3 times x, so it's 3 times 0.5 plus 1 over 0.5. So we're replacing x with 0.5. So y would be equal to 3 times 0.5. That's 1.5, right? Plus 1 divided by 0.5, that's 2. So 3.5. So when x is 0.5, the y value should be 3.5. Alright, using this equation, that's how we get the missing values. Let's get the missing value now for when x is 2. So when x is 2, y equal to 3 times 2 plus 1 over 2. So y is equal to that. This is 6 plus a half, that's 6.5, right? So that's 6.5. So when x is 2, y is 6.5. On the diagram on page 25, the ordered pairs shown in the table have been plotted, except for the missing ones. Using your answers in A part 1, plot the missing points and connect all the points with a smooth curve. So we have plotted the 2 missing points were 0.5, 3.5, and 2, 6.5. So here's our graph. So we're plotting 2 points here, 0.5, 3.5. So 0.5 will be going over. 0.5 is half of the 1. That's half of 1, right? 0.5. And we're going up 3.5. So 0.5. That's midway between 0 and 1. Up to 3.5 should be somewhere there, right? And the other point was 2 and 6.5. So here is 2. So 6.5 will go up to 6.5. That's there. So it will be there. And now we're asked to draw a smooth curve by connecting all the points. So it's a curve, so no need for a ruler here. So let me try draw a curve. All right, that looks, I guess it could be smoother, but that will do for now. And here's also this section, just, all right, that section there. And up there. All right, so I guess that's the curve. That's what we're asked to do now. And then we're asked by part 3, by drawing an appropriate straight line on the diagram on page 25, find approximate solutions to the equation 3x plus 1 over x equal to 6. So notice this was the equation that we circled. So notice 3x plus 1x equal to 6, which means that y is equal to 6, because remember I know y equal 3x plus 1 over x. And we are told that 3x plus 1 over x equal to 6, which means we're drawing the line y equal to 6. Let's draw that line and see where it intersects the curve. So the line y equal to 6 would be this line that cuts the y-axis at 6. So it would be this straight line. And of course, it's a line, so you're using a ruler. And you use where the line intersects the graph. All right, intersect the graph at 2 points. So we can draw straight lines come down from here. All right, to see where these lines now cut the x-axis. I must come down here, and there's an approximation. All right, there's an approximation. I guess your graph will be smoother than mine. So if I should come down here, approximately. So this is a, notice on the x-axis, each box you're going up by 0.2, 0.2, 0.4, 0.6, 0.81. So this is approximately 0.2, or this is approximately 1.8. So the solution here, using the graph, would be x equal to 0.2 and x equal to 1.8. So in part B, the speed time graph below shows information on the first 60 seconds of a car's journey. So the speed on the vertical axis, meter per second, and we have time on the horizontal axis. And we also calculate the acceleration in meters per second square of the car during stage B. Now remember that acceleration A is equal to change in speed over change in time. Alright, so let's see how much for stage B, let's see how much the time and the speed change by. So for stage B, there is stage B. So for stage B, notice the time. Well, let me do the speed first on the vertical axis. So on stage B, the initial speed was 15. Notice midway between the 20 and the 10. So 15, and the final speed was what? 40. So the change in speed would have been 40 minus 15. Let me just insert that. And the change in time at stage B, the change in time, notice for time, the initial time was 40 seconds, and then stage B ended 60 seconds. So the change in time would have been 60 minus 40, that's 20 seconds. So the acceleration would have been 25, 40 minus 15, that's 25, and 60 minus 40, that's 20, which is equal to 25 divided by 20, that seems like 1.25. So that's 1.25 meter per second square. Part 2, calculate the average speed of the car during stage B. Now average speed, let me just follow the form for average speed. So average speed is equal to total distance covered over the time taken. Alright, let's find the average speed of the car during stage B. Now for a speed time graph, the total distance covered is area under the graph. So remember, we only want it for stage B. So stage B begins here. Let me just use that. Alright, and stage, so alright, so now we have, this seems like a trapezium. Let me just break it up into a rectangle and a triangle. Alright, so the total distance covered, it would be area under the graph. Let's find the area of this rectangular shape here now. Notice the length here is between 40 and 60, so the length here is 20, and so this is 20, right? And this we're so 0 to 15, right? So 15, so this is 15. So 15 times 20, 15 times 20, that's what? 350. The area of this part is 350. Now the area of the triangular part here, so it is 20, half base times height. Alright, half base times height. This is 20, just as here. So half of this would be 10. What's the height now? The height is, we are moving from 15 to 40, right? We're moving from 15 to 40. So the height is what? 25? So the height is 25. This is also 20. So half base times height, area of a triangle, half base, so half of 20 is 10. 10 times 25 is 250, right? We made an error here. 20 times 15 is actually 300. Alright, so the area of this part is 300 and the area of this part is 250. So the area of the entire area under the graph here on the stage B would be 250 and 350. That's 550. So which means the total distance covered will be 550 meters. Alright, and the time taken, just another glance at the graph, notice the time taken to complete stage B. We move from 40 seconds to 60 seconds, so the time taken will be 20 seconds, right? So it'll be 20 seconds. So the average speed would be 550 divided by 20. That's 27.5 meters per second. At t equals 60 seconds, the car starts to slow down with a uniform deceleration of 2.5 meters per second square. How long will it take the car to come to rest? Alright, so remember we have a formula here, acceleration equal change in speed over change in time, right? With time. Now talk about change in speed. So at t equals 60 seconds, so I'm gonna put initial speed minus final speed. over the change in time, which is what we want to try to find, right? Now, the acceleration we're told is the car is decelerating, which simply means that the acceleration is negative. Remember, acceleration is what we call a vector quantity, so direction matters. So because it's slowing down, we use a negative 2.5 to show that the car is actually slowing down, right? The initial speed at 60 seconds, the car was traveling at what speed? Let's check. At 60 seconds, the car was traveling at 40 meters per second. So we use 40 for the initial speed because initially we are beginning at the time we're t 60 seconds, right? The final speed is when the cars come to rest. When the car come to rest, that would be final speed, which means when it come to rest, that speed will be 0, right? Over t. All right. I guess we could stay use 2.5. Just don't recognize that it's really a deceleration. All right. So let me just. So this will be 2.5 equal 40 over t. All right. It's over 1. If I cross multiply, 2.5 times t, or you say multiply both sides by t. Multiply both sides by t, right? Here's the same result. Multiply both sides by t. So 2.5t is equal to 40. And to get t, we divide both sides by 2.5. So t equal 40. Now what's 40 divided by 2.5? That's 16. So the car would come to rest. Once you start decelerating, the car would come to rest after 60 seconds. All right. In other words, from when it initially started, it come to rest 76 seconds, right? Because the original journey was 60 seconds, and then it comes to rest 16 seconds after that. So from when it started to when it finished, I guess it's 76 seconds. But from this time at 60 seconds, it would come to rest 16 seconds after the 60 seconds. All right. So in other words, the total time for which the car was in motion would have been 76 seconds. So we're now at number 9. So the diagram there, the relative position of 3 reservoirs, B, F, and G, all on level ground, and we're given some distances and we're given some angles and some bearings there, right? We are asked now to calculate the bearing of B from F. The bearing of B from F. Which angle is that? So we comment the bearing of B from F. So if it's from F, technically it's from the north of F. So the bearing of B from F. So it's from the north of F. Alright. That's what would be the north of F, right? So bearing of B from F, so would be this angle. Will be all of that angle, right? In blue. Well, we know this is at 103 already. So now we need to find this angle here. So let's see, we can do some extension. Now if I extend this out, if I extend this down here, then these are alternate angles. So this angle will be 42. This angle will be 42 degrees. Right, alternate angle to this angle. Now angles in a straight line add to give 180. So this angle will be 180 minus 42, which is what, 138. And then this angle, let me use a different color, use yellow. This angle, you can get this angle now. So remember, it's a for the complete turn there. It's 360 degrees, right? So this angle that I color in yellow will be 360 minus 103 minus 138, which would be 119. So this angle will be 119 degrees. So the bearing of B from F, the bearing of B from X will be the 119 plus the 103. So bearing of B from F would be, this would be equal to 119 plus 103 degrees, which would be 222 degrees. Of course, there are alternate ways to get these angles, but whatever, it should come to 222. Next, we're also calculate the distance BG given your answer to one decimal place. So BG, let's look back at the shape again and see which line is BG. So here's BG. So to calculate BG, of course, we can use a cosine rule. Let's use a cosine rule. Applying the cosine rule to that triangle here. So BG square is equal to 32 square plus 55 square minus 2 times 32 times 55 cos the angle opposite to BG, which remember all of this angle, which is 103 degrees. And of course, your calculator can write that for you right away. No need to break it into pieces. So we enter all those values in the calculator as they are, and we end up with BG square is equal to, alright, which means that BG would be equal to the square root of 4840.828, which would be 69.6 kilometers, of course, to one decimal point, right? So BG should be 69.6 kilometers. Calculate to the nearest degree or whole number the bearing of G from B. The bearing of G from B. Let's look back at the diagram. The bearing of B from G. Sorry, it's the bearing of G from B. So from B, so that's here, from B to the line that goes to G, right? So that's the angle that we want. So we know this angle is 42, so what we want is this angle inside. And to get this angle inside, of course, we can certainly use the sine rule. So we can say the sine of this angle, let me call it angle B here. So the sine of angle B over the opposite side, which is 55, is equal to, let me choose another side, the sine of this angle here, which is 103, over the opposite side, which is 69.6. And of course, for us to get angle B, we need to find sine B first. So we can times both sides by 55. So 55 times the left and 55 times the right. So that into that, yes, which means that sine B is equal to 0.77. And you can second function or shift and inverse. B would be equal to 50 degrees. So this angle would be 50 degrees, which means the bearing of G from B would be 42 plus 50. So that would be 92 degrees. Well, right, using 3 digits, right? 92 degrees. So part B deals with circle theorem. We are also find 3 different angles with reasons, of course. So angle ABC, angle CMB, angle NCM. Let's deal with them one at a time. So angle ABC, that's this angle, ABC, that's this angle. No, remember, if two lines are subtended from the diameter, notice AB represents the diameter of the circle, and we have two lines subtended from the endpoints of this diameter to meet on the circumference, which means that this angle is a right angle. So the angle the triangle ABC is a right angle triangle. And remember, all angles in a triangle, the sum of the angles add to 180. So this angle ABC would be equal to so these two angles must add to give 90. This is 90, so the other two angles must add to give 90, because all angles add to 180. So this angle would be 90 minus 58 degrees, which would be 32 degrees. Note, if this is 32, when you add 58 plus 32 plus 90, you should end up with 180 degrees. Now angle CMB, that's this angle. Notice it's part of what we call a cyclic quadrilateral. Alright, notice if you look at A, B, M, C, that's a quadrilateral within the circle. So notice with the cyclic quadrilateral, one of the theorems, that the opposite angles must add to give 180. So the opposite angles are what we call supplementary angles. They must add to give 180. So CMB would be 180 minus the 58, which is 122 degrees. So this is 122 degrees, as these two angles must add to give us 180. They are opposite angles in a cyclic quadrilateral, which is simply a quadrilateral inside of a circle, where all the vertices are touching the circumference of the circle, right? Now angle NCM, that's which angle? So NCM, that's this angle. Alright, let's try to figure out this angle. Now this angle, let me use a different color. Let me use this color, alright? So this angles on a straight line add to give 180. So if this angle is 122, then this angle would be 58 degrees. Notice angles on a straight line add to give 180. So this angle would have to be 58 degrees. Alright? And notice NCM is actually a right angle triangle. As you see, this is a right angle. Alright? So this is 90, this is 58. So this angle must complete the sum total for everything to come to 180 degrees, right? So this is 90. So this the angle in the blue here and the angle 58 degrees, these two angles must add to give 90. So NCM would be 90 minus 58 degrees, and that would be actually 32 degrees. So this angle will be 32 degrees. Notice when you add 32 plus 58 plus 90, you end up with 180, which is what the sum total of the angles in a triangle must be equal to. So question 10, which is our final question. Transformation T is defined by the matrix T equal to 2 minus 1, 2, 0. The point A minus 2, 3 is mapped onto the point A image AB under the transformation T. Find the value of A and of B. So the point A is mapped onto the image point AB under T, which means that if you should multiply, which means that T times A gives you T image. I'm going to put that in a matrix form now. So t was what? T was 2 minus 1, 2, 0. We'll multiply that to the point A, which is minus 2, 3. You should end up with AB. Let's do the multiplication now. So remember it's rows by column. So 2 minus 1 times negative 2, 3, negative 2, 3. So it's actually 2 times minus 2 plus minus 1 times 3. And then you multiply 2, 0 now by the same column over here. So it's 2 times minus 2 plus 0 times 3 equal to AB here, which means that 2 times minus 2, let's put it here, that's minus 4, and so minus 4 plus minus 3, because negative 1 times 3, that's negative 3, right? So it's negative 4 plus negative 3, that's negative 7. 2 times 2, that's 4, 4 plus 0, 4. So which means that A is equal to minus 7 and B is equal to 4. A slight error was made there. So 2, 0 times negative 2, 3 is 2 times minus 2 actually. So this would be actual this would be minus 4. Hence the value of B is minus 4. So A is minus 7 and B is minus 4. Next, we're asked to determine the transformation matrix that maps A image to A. Notice T. Just remember T. Remember T maps A to A image. So now we want the matrix that maps now A image back to A. And of course, that would be the inverse of T. Alright, that would be the opposite operation. So remember T was, let me just rewrite T was 2 minus 1, 2, 0. So T was 2 minus 1, 2, 0. So we want the inverse of T. Now the inverse of T is 1 over the determinant of T times the adjoint of T. Now the determinant of T, let's put the determinant of T here. To the determinant of T, we can just cross multiply and subtract diagonal. So it's 0 times 2, which is 0, minus 2 times minus 1, that's minus 2. So the determinant is actually positive 2, minus minus. So T inverse would be 1 over the determinant, so 1 over 2. And the adjoint, for the leading diagonal, this element swap places, and the other diagonal elements change signs. So we multiply each of those values by a half. So half of 0, that's 0. Half of 1, that's half. Half of minus 2, that's minus 1. And half of 2, that is 1. So this is a matrix that maps A image back to A. Alright, so T image, this matrix maps A image back to the original point A. So another transformation P is defined by the matrix 0, 1, 1 minus 2. Find the single 2 by 2 matrix that represents a combined transformation of T followed by P. So T followed by P, we represent that as PT. Alright, so T followed by P. Alright, so P is 0, 1, 1 minus 2. And remember the matrix T was, what was it, 2 minus 1, 2, 0. So we'll do the multiplication, right, row by column. So we take 0, 1 and apply it to 2, 2. So 0 times 2, that's 0, plus 1 times 2, that's 2. Then we apply 0, 1 to negative 1, 0. 0 times minus 1, that's 0. 1 times 0, that's also 0. Then we take the bottom row and apply it to the same two columns over here. So 1 times 2, that's 2, plus minus 2 times 2, that's minus 4. And it was 1 minus 2 times the final column, negative 1, 0. 1 times minus 1, that's minus 1. Plus negative 2 times 0, that's 0. So the single transformation of t followed by p would be 0 plus 2, 2, 0, minus 2, and minus 1. Hence find the image of the point 1, 4 under this transformation. So the image of the point 1, 4 under this transformation. You simply just multiply the transformation to the point. So 2, 0, minus 2, minus 1 times 1, 4. We will end up with, so row by column, so 2 times 1, which is 2, plus 0 times 4 is 0. Then bottom row by the column, so minus 2 times 1, that's minus 2, plus minus 1 times 4, that's minus 4. So we'll end up with 2 minus 6. So the image point would be equal to, 2 minus 6. So the diagram below, not drawn to scale, shows a quadrilateral ABCD in which AB is M, DC is 3M, AD is N. Complete the statement below on the geometric properties of the following vectors. Vector AB and vector DC are parallel, as you can see. Vector DC is 3 times vector AM. So we see they are parallel. The length, the magnitude of AB, is notice the magnitude of AB is actually less than the magnitude of DC. So the magnitude of DC is 3 times the magnitude of AB, which means the magnitude of AB is actually 1/3 times CD. Careful. And part 2, express BC in terms of M and N. BC, let's go back up to the diagram. Express BC in terms of M and N. So I will do this part up here, BC. So BC, of course, we want to find BC. So now notice BC, to get from B to C, if you're at B and you want to get to C, you can go directly from B to C, or you can say it's B to A, then A to D, and then D to C. Alright, so BC, so notice A to B is M, so B to A will be negative M. So remember with vectors, direction is very important, alright, because we're going in opposite direction. A to B is M, as we can see here, so the opposite direction, B to A, is minus M. So this negative sign means the direction is different, right? Opposite direction. A to D, same as direction here, so A to D is N. Of course, D to A would be negative N, but A to D, that's what we're interested in, plus DC, DC is 3M, as we see here, DC is 3M. And of course, we can group like terms. So negative M plus 3M, that's 2M plus N. So BC, the vector BC, in terms of M and N, is 2M plus N. And final section, L is a midpoint of CD, and find BL in terms of M and N. So L is a midpoint of CD, and we also find BL. So let's go back to the diagram. L is a midpoint of CD. Alright, so here we have L. and is the midpoint of, we have L here, is the midpoint of CD. What we're asked to find again? BL. Yeah, we're asked to find BL, which would be. So this should be straightforward to find BL. So B to L. To get from B to L, we can go B to A plus A to D plus D to L. Alright, so we want to reach to DL, right? So now, which means that, so BL is BL, right? So B to A, again, minus M, we explain why already. A to D, that's positive N, same direction, plus DL. Now we are told L is so DC is 3M. Alright? But we're not going the entire length here. We're going to go in half of that, right? So it's half of 3M. So it's half of 3M. What's half of 3M? 1.5, right? Which is 1.5 M. So the full DC is 3M, but we're stopping at L, and L is midway, half in the middle, right? So it's 1.5 M. So we group like terms, negative 1M, negative 1 plus 1.5, that's positive 0.5, right? So positive 0.5 M, or if you want to call half M, plus N. And that would be our vector BL. And there goes June 2018 CSEC Mathematics past paper. We can put our half M plus N, right?